In this video, we will be looking at some of the applications for trigonometric functions, specifically angular speed and also linear speed. To start that conversation, we will talk about radians versus degrees and then arc length. Most of you have had a trigonometry class before this, and so you're familiar with the unit circle. The unit circle is going to specifically have a radius of 1, and so as a result, the circumference is going to be 2 pi. As a reminder, the formula that we use for circumference of a circle is pi times the diameter. And if the radius were 1 in a circle, then the diameter would be 2, right? Twice the radius. So that's how we're getting that circumference of a unit circle is equal to 2 times pi. This set of pictures here is just showing you that if a point were to travel part of the way around the circle, we get these different measurements. Halfway would be pi, for example, and an eighth of the way would be pi over 4 and so forth. When we have an arc that in measurement is exactly the same length as the radius, that is the definition of 1 radian. Now, again, those of you that have had trigonometry before, you know that radians also often have the pi symbol in them. If I were to go, let's say, halfway around the circle, we would say that the measurement there would be pi radians, or it would have the same value as 180 degrees, is sort of that way that we think about going back and forth between them. But if you think about the number associated with pi, that number is 3.14. And so the distance that you would have traveled is approximately a little bit more than 3 radian. So if we kind of take that idea and extend it to where 1 radian would be, we see that 1 radian is about 57.3 degrees. Again, looking at this picture back over here, this original picture, it does look like that red arc that we see, or the angle that's been opened, is approximately, looks like it's close to 60 degrees, so we're getting that 57 degrees. The numbers of radians are much smaller than we're used to seeing in degrees. And remember that when you list a value for radian, like here in this third example, we have 4.71 radian. We don't put the degree symbol. So if you mean for a measurement to be in degrees, you have to put the degree symbol. Otherwise, it's assumed to be radians. So as we were just mentioning, if we want to convert back and forth between radians and degrees, we use the conversion that pi radians is equal to 180 degrees. So for example A, if I wanted to start with negative 135 degrees, I'm going to write it as a fraction. And then what I'll do is I'll multiply by one of these unit conversions. A unit conversion is when you have two items that are equal. One goes in the numerator, one goes in the denominator, and what you're doing is effectively changing the units or the measurement that we're using. I want the degrees to go on the bottom so that degrees will cancel top bottom, and so I'll put the pi radians on the top. Again, I'm just deciding which way to write the fraction based on what unit I'm trying to end up with. So plugging this into a calculator, I'm going to just type in 135 over 180, and that's going to give me 3/4. So I'll have negative 3/4, and the pi symbol I'm just kind of leaving there. If I type the pi symbol, it's going to change it to a decimal. So this would be the exact answer, negative 3 pi over 4. And again, since I don't have the degree measurement, it's implied to be radians. When I look at something like letter B, I don't have a number that we typically see as one of the ones we remember from the unit circle, so we know that this one isn't going to end up being a nice fraction. but I can still follow the same process. I'll put 157 degrees in the top of a fraction, and I'll multiply by pi radians over 180 degrees. In this case, I'm going to type in the 157 times pi, divide it by 180, and I get approximately 2.74 radian. Let's think about where 157 degrees is if we were to look at that on the unit circle. 150 degrees or 157 degrees is going to be maybe over here somewhere. And based on what we were talking about a minute ago as far as like 1 radian, 2 radians, we're saying that 1 radian was going to be maybe about here. And then this would be about 2 radians. And if we go all the way here back to the x-axis, we would have 3.14 radians, right, or pi. And so it kind of makes sense to me, just looking at where this value is ending up, that this is going to be about 2.74 radians. Just kind of estimating and trying to understand how the units are changing. For the last example on this page, we're looking at 63.59 degrees, and I'll multiply by pi radians over 180 degrees. Plug that into the calculator, and I'm getting about 1.11 radians. And that kind of makes sense because we saw that 1 radian was just under 60 degrees. I'm going to assume that you all have access to a unit circle. I've posted one on Canvas, and these are some of the common equivalents between radians and degrees that we come across frequently on the unit circle. When we have the arc length, which is the length going along the circumference of the circle, compared to the measurement of what we call the central angle, the angle that's sitting in the center of the circle, or in this case on the origin of the x and the y axis. When the radius is equal to 1, we kind of equate that arc length with the central angle, but they're actually measuring two different things, right? One is how far an angle is opening in degrees or radians, and the other is a distance along the outside of the circle. And so the relation that we have between these two, you can see here in this formula here, that the angle, the central angle, is going to be the ratio of the arc length over the radius. When the radius is 1, these two are equal to each other, right? Which we see in the unit circle, that the angle is equal to the arc length. And so when we think about a picture like, let's say if I went 1/8 of the way around the circle, I would be at pi over 4. Well, that's the same thing we would say that this angle here, we would say that that angle is pi over 4. And that's because the radius is equal to 1. So in this equation here, we're just having theta equaling s. But we don't always, in application problems, have the radius equaling 1, and so we want to remember this relationship. All right, so we'll use this idea for a couple of examples. Let's find the length of an arc of a circle. It has a radius of 16 centimeters. That's associated with an angle of 5 pi over 4. I'm going to draw a picture first to just think about what's happening here. We have a circle with a radius of 16 centimeters, and 5 pi over 4 is going to be over, I'm going to put little tick marks for the axes. It's going to be over here, right? So going like all the way around, right? So that's going to be 5 pi over 4. I'll write it here. 5 pi over 4. So the question is, how long is this arc? Well, one way to think about this is, what is the circumference of this circle? The circumference is pi times the diameter. In this case, that would be 32 pi centimeters. And how far around the circle are we going? We're going, let's see, half plus an eighth. The total distance we're moving, I'm thinking we're going, the distance is 1/2 of the circle, 1/2 of the 2 pi, which is pi, right? Or 1/2 of the total distance, plus 1/8 of the distance, which is 5/8 of the total distance of the circumference. So what if I did 5/8 times 32 pi? I'm thinking it's 5/8 of the distance around the whole thing. Let's do 5/8 times 32. I'm going to leave the pi symbol out. And I get 20 pi. This is what I, just kind of looking about the picture, this is what I think the arc length is going to be. Let's look back at the slide before and use instead, if we use this formula, the formula that they gave us was theta equals s over r, and we're trying to find s, we're trying to find the arc length. So rearranging this formula, we have that s, the arc length, is equal to theta, the angle, times the radius. So if I do it that way, I get that, s is equal to 5 pi over 4 times the radius, which is 16. Notice that the numbers are similar, but they're just off by a half. That's because the circumference, because we have that factor of 2 that's coming into play. And so same thing, if I multiply this out, I'm going to get 20 times pi. Most of the time, you will probably think about this formula that they've been given, but if you want to just think about it in terms of the circumference of a circle, you can figure it out that way as well. Looking at number 2, they give us the radius of a circle. Oh, they want us to find the radius of the circle. They're giving us the intercepted arc, so that's s. And the central angle is 2 pi over 3. Whenever we do application problems for things involving angles, we use radians rather than degree measurements. So we're trying to find the radius. Our formula is theta equals s over r. Rearranging this, we have that r is equal to r times theta is equal to s. And so then r is equal to s over theta. This is the version that we want to use. So in this case, the radius is going to be 6 pi divided by 2 pi over 3. I know the pi's are going to cancel. That fraction in the bottom is going to flip upside down. And I'm going to end up with the radius being 9 inches in this case. The next topic we're going to be looking at is linear versus angular speed. There are a couple ideas that I want to share with you for those of you that don't remember this from your trigonometry class. Linear speed is the distance around the outside of a figure. So linear speed would be if I had, say, a point that started here and it was traveling along the outside of this circle, how fast would it move? Versus angular speed would be I started with some angle and it's rotating around, right? Maybe like a bicycle spoke. How fast is that angle changing? So those are two different measurements. And this slide is actually relating the two of them together. Key things to note is that we use the variable v for linear speed. We use the variable omega. This is a Greek letter omega. It's a lowercase. We use that for angular speed. And the units for the distance for the radius and the linear speed have to be the same, right? They have to, if they're both feet, they have to match. And similarly for time, if I'm talking about like feet per second, the angular speed would be, radians per second. So we need the units to match in these equations. Okay, so the way that we get to this formula here is through a series of other things that we sort of already know. I want to talk about the things that we sort of already know. We know that when we were talking about a linear speed or just speed in general, I'll write it this way. Speed is equal to distance over time. You calculate this all the time when you're going on a road trip or something, right? How far did you drive? How much time did you take? That would be your speed overall. And we write this mathematically as v equals s over t. S is the variable we use for distance, t is the variable for time, v is for speed or velocity would be another way to think about that. Angular speed is going to be the angle, how much the angle has changed over a particular point in time. Mathematically, we write that as omega equals theta for angle over t for time. And then the last formula we just learned was for arc length. And that was equal to the radius multiplied by the angle. So S is equal to R times theta, all right? So combining these together is going to get us to this formula that I have highlighted up here, which relates linear and angular speed together. We want to know how, as a tire is rotating through a particular angle, what's the distance that's being traveled, which can be measured by a point on the outside of the tread of the tire, right? We want to know how to relate these two. So combining these together, I'm going to start here with the original one that tells us speed. And then what I'm going to do is take this here and substitute that into S. So instead of writing S, I'll write R theta over T. Then what I'm going to do is separate these. I'm going to take the radius and put it up on its own and then have theta over T on its own. So that then I can go up here and I can make an exchange here. So then I have that linear speed is equal to the radius times the angular speed. And again, this is just the derivation of how we take ideas that we know, combine them together to relate linear and angular speed. All right, let's do a couple of examples. The Earth, a satellite is orbiting the Earth 1,200 kilometers above the Earth. So we have Earth like this. We've got some satellite out here that's orbiting. And we know that this distance here is 1,200 right? They want us to use this distance here as 6,400, or that's the approximate radius of the Earth. My drawing is obviously not to scale. And then we also know they gave us the angular speed, right? They told us that for the satellite, it's traveling one complete rotation. So that's going to be, it's going to go through an angle of 2 pi all the way around in 90 minutes. So that's the angular speed. We could simplify this to be pi over 45 minutes. Okay. So we want to find the linear speed, and we just had a formula a minute ago that would relate the linear and the angular speed. The radius that we're going to use, we've got to add the radius of the Earth and then also the distance out to the satellite. So that's going to be 7,600 kilometers. And then we're going to multiply that by the angular speed, pi over 45 minutes. And then plug that into the calculator. And you should get about 531 kilometers per minute. It's really fast. All right, let's look at another example, angular speed. A car is traveling at a speed of 70 miles per hour. And they gave us the diameter of each of the tires. And we want to find the angle that the tire travels through within every 10 seconds. Okay. So what do we know? The speed is 70 miles per 1 hour, right? The tire measurement that they gave us is in seconds, so we need to do a little bit of math here to change this velocity into feet per second, right? We've got inches for the diameter, and we've got seconds here for what they're wanting us to find. So I'm going to first switch this to feet. So I'll do a conversion here. Let's do 1 hour over 60 minutes, 61 minute over 60 seconds. I'm changing it into seconds. And then I'm going to also change the miles into feet. 5,280 feet in 1 mile. Again, I'm using different unit fractions. I know that I want the mile to cancel with the mile, so I write that fraction so that the ones in the denominators it'll cancel. I know that minutes and minutes will cancel, hour and hour will cancel, and so I'm left with feet per second. Plug this into the calculator. You're taking 70 over 60 over 60 times 5,280 and get about 102.67 feet per second. We just changed the velocity into a metric that's going to make more sense for our other calculations. The radius is 30875 divided by 2. Which is 15.4375, and again that was in inches. But we want to change it into feet, so we'll multiply by 1 foot over 12 inches. And so we're getting about 1.29 feet. Okay. I think we're ready to calculate now. We're trying to find the angle. We know that the angular speed is equal to the speed 102.67 feet per second over the radius 1.29 feet. So we're getting, plug that into the calculator to get approximately 79.59, this is going to be in radians per second. And then for our final step, we want to find the angle. So we found the angular speed, 79.59, and we're going to multiply that by the time that they gave us, which was 10 seconds. And so that's about 796. And that, again, that measurement is going to be radians. All right, thanks for watching. If you have questions, send me an email and I will see you in class.